Welcome back, Nature in Code. We're in chapter 3, and today we're going to talk about the effective population size. So we just learned some of the profound consequences of genetic drift. A loss in genetic variation dependent on the size of the population. And I mentioned at the end of the last lecture that there's an important concept to understand in the context of genetic drift, and that's the concept of the effective population size. So before I'm going to explain it in detail, I just want to give the definition that I generally use. So the effective population size is the size of an ideal population that shows the same decay of genetic variation as the actual population of interest. Now that's a bit of a mouthful, but still, let me just repeat this. Okay, this is the size of an ideal population that shows the same decay of genetic variation as the actual population of interest. And rather than talking about this or even spelling this out, I want to show you with a graph. Okay, so this has to do with the decay of genetic variation depending on the population size. So let's visualize this. So let's plot here this measure of interest, which is H, as this measure of genetic variation, and here we have time, okay, or generations. Generations. Okay, and so now say you observe a population, and you observe that it changes over time. That in particular, that its genetic variation decays over time, as you would often expect under genetic drift. So you might maybe measure something like this. Something like this, some form of decay. I mean, it's probably going to be more chaotic, but this is an example. Okay, so this is your actual, so these points refer to your actual measurements. Okay, this is your actual population or your census population. Okay, and the census population has a size of, say, 200 individuals. Now, let's say you use this value now. You say, okay, I have 200 individuals, and I learned about these formulas to understand the genetic drift effect of populations of size 200. So you're going to plug this number into the formula that we just developed, and you would see maybe something like this. And I'm just going to use a red line here. You maybe see something like, oops, excuse me, something like this. So this now, okay, is what we called an ideal population. This is what you get in the model situation. Okay, because remember, we make a lot of very simplifying assumptions about the population structure. And essentially, we assume no sex differences. We assume non-overlapping generations. We assume no spatial structure. We assume this very sort of almost gas-like population, but the only difference is that now we have a finite population size. However, it's still very idealized, and that's why we call it an ideal population. And so if you plug in this value here, you would get a decay that is actually much slower than the one that you actually observe. And indeed, and I'm going to use the blue color here, if you fiddle around with the numbers a little bit, you'll soon find that the best fit would be a case where you have an ideal population size of 100. Okay, and that this would be this dashed line here. So, and what that means, right, is that your population that has 200 individuals, in fact, behaves as if it were an ideal population of size 100. So that's how this definition comes about, right? The size of an ideal population, so in this case 100, that shows the same decay of genetic variation, yeah, as the actual population of interest, which in your case is here with the population in black. So that is the effective population size. And so it's very important to understand this concept, because you would think your population is of size 200, and of course you're correct, but that is your census population size. It's very tempting now to just go and say, okay, my population is of size 200, and now I can use all these formulas that we developed and all this theory, and I can plug in this number, and this will give me, a prediction of how my population is going to behave. No, that's not true. Actually, what you need to understand first is, what is the effective population size? Your population may have 200 individuals, or however many individuals, but it may actually behave as if it were a 100 individual sized population. And now you can use this number to calculate various properties and make various predictions. So in some sense, this is like a correction factor, right? I mean, you count a certain number of individuals in your population, but then before you go on and make now certain predictions and perform calculations, you need to correct it, and you need to work with the effective population size. And so you may think, well, okay, but is that really so important? What's the difference? And to understand that, I'm going to give you one example here that will show just how profound these differences can be. And as a rule of thumb, usually the effective population size is much smaller than the census population size. Okay, so the effective population size is usually smaller, and sometimes, in fact, drastically so, than the census population size. And just be aware that whenever we talk about the population size here in the context of theory, we actually always talk about the effective population size. To some extent, from a genetic perspective, it doesn't actually really matter how many individuals there are in your population. The only thing that matters is how many individuals are there effectively from a genetic perspective. So one major factor that I'm going to here develop with you is that of a population bottleneck. So far, right, we have assumed, if you look again here at time, and now if you look at the population size here, we essentially have assumed a straight line, right? We have modeled this with, say, n,000 or n,2000, but it's never changed. We have essentially assumed that this is constant over time. But in reality, that's often not the case. In reality, in fact, you have fluctuating population sizes, and sometimes you may have relatively stable population sizes, but then some catastrophic event and your population drops dramatically, and it may rebound very quickly again. And so these are so-called population size bottlenecks, right? And they can occur for various reasons: predation, disease, what have you. What I want to do now is I want to develop this idea of a bottleneck and show you what the effect is on the population size. And we're gonna sort of build a toy model again, as always, right? Because we want to keep things very simple. So we're gonna assume we have here a constant population size, and then just for one generation we have this dramatic drop, and then it rebounds and goes back to exactly the same value. And so again, a population size, and here's time. And we would now like to understand, what is the effect of that population bottleneck. So let's just say we look at the at 3 generations here: the generation of the bottleneck, generation before, and the generation after. And say we have population size 1,000 here, and then it drops to, say, 10 individuals, and then it jumps right back to 1,000 individuals. Okay, so what is the effective population size here in this time period of these 3 generations? Now, it's tempting here just to say, well, I mean, I have 1,000 individuals, the first here in this generation, and then I have 10, and then in the following generation I have again 1,000. So the average of that is roughly 670 individuals, right? 2010 divided by 3, so roughly 670 individuals. Now, it's tempting to do that because we're just used to taking averages, and this is, in mathematical terms, this type of average is called the arithmetic mean, where you just add up all the numbers and then you divide by the number of numbers that you actually have. Well, it turns out that the effective population size of a population that changes in size is not the arithmetic mean; it's the harmonic mean. And the harmonic mean of a population, harmonic mean of certain numbers, say, you have x1, x2, x3, and so on up to xn. So the harmonic mean of this set of numbers is n divided by 1 over x1 plus 1 over x2 plus 1 over x3 plus and so on, until you come to 1 over xn. So that is the harmonic mean. Now, what is the harmonic mean here in this case then? Well, let me just delete this here and just basically use this formula to calculate the value of the effective population size here. So it is 3 over 1 over 1,000 plus 1 over 10 plus 1 over 1,000. And that is, if you calculate this, very easy to see, right? This is 0.001, this is 0.1, and this is 0.001. So taken together, right, these are 0.102. And that is approximately 30. Okay, and I'm going to put an exclamation mark here because this is quite remarkable, right? What this means is that the effective population size is 30, and you could have been forgiven for thinking the effective population size is the arithmetic mean, the average, which would be 670, but you would have overestimated by more than a factor of 20, so quite substantial. And if you think about it, let's say we had started here with 10,000 instead of 1,000. Okay, so just add a 0 here. So now, of course, this number would have been 6,700 approximately, and here, okay, we would have 1 over 10,000, and so here we would need to add a 0 as well. Okay, I'm just going to add it here, and so this would have been not 0.102, but 0.1002, which, doesn't really affect this number here. It's still approximately 30. But so now, actually, you would have overestimated, and I don't know why I'm laughing, because it's not really funny, but it's stunning, right? You would have overestimated this by a factor 200. So you think, oh, I got 10,000 individuals, then severe collapse, 10 individuals, then again 10,000 individuals. Nah, average is about 6,700 individuals. No, this population will behave from a genetic perspective as if it had been on average 30 individuals. I mean, this is quite stunning, isn't it? And if you think about this a little more, I mean, we could continue this. I could say, you know what? Let's add this. Let's assume we would have had 1 million individuals. well, it doesn't matter, right? The larger that number here in the denominator, the smaller that number here. And so the less important the effect. Really, the only number that's driving here is the small number here, right? This is 1 over 10. That's the only number that's driving this small value. And so really, it doesn't matter what your population size is up here. The bottleneck here is completely driving the genetic fate of this population. And so I hope this sort of brings home the main point. So this can be quite substantial. It's not just sort of a semantic difference, the number of individuals that you actually count versus the number of individuals in an ideal population. No, this can be truly substantial, right? And here's an example where you would overestimate your population size by factor 200. So this population will not at all act like a population of 6,700 individuals from a genetic perspective. It will behave like a population of 30 individuals. And as you know, that can have very substantial consequences for genetics. So that's the theory behind this. That's the theory behind the effective population size. It's the theory behind things like bottlenecks. Now, when I first learned about this back in the day, I thought, well, that's quite stunning, and I was fascinated by it. But I sort of had to take this at face value. It's like, okay, the effective population size is the harmonic mean. All right. Sounds good to me. However, you're in a much better situation, right? Because we just developed a couple of lectures ago a stochastic simulation of genetic drift in JavaScript that runs in your browser and even on your smartphone if you have a modern smartphone. So now we can go back and modify the simulation a little bit, and we can implement bottlenecks and see what happens. And as you'll see in the next lecture, when we implement this in JavaScript, this is exactly right. The population will indeed, from a genetic perspective, behave as if it were the size of its harmonic mean. So I'll see you in the next lecture.